4.9 Lesson 1, Related Rates. Our objective for today is that you will be able to solve related rates problems by following the guidelines. And these are the guidelines that we have for solving related rates problems. 1, 2, 3, 4. 1. Identify all given quantities and quantities to be determined. So in a problem, not just related rates problems, but any math problem, you have some given information. So what do we know? And what do we want to find? Make a sketch and label the quantities. So these are things that will help you understand what these problems are asking you to do and do them successfully. So this step is not particularly that much different from what you've been doing in pre-calculus when you're dealing with the word problem, just trying to understand what you know, what you're trying to find, and sketching a diagram labeling quantities. But it is critically important, especially for problems having to do with related rates. Guideline number 2, write an equation involving the variables whose rates of change either are given or are to be determined. And I'll make a note here. This equation is actually an equation that involves variables but not their rates of change. So this equation does not involve any rates of change. This equation does not have rates of change. It doesn't have derivatives. And you'll see that when we look at our example. And then step 3, or guideline 3, using the chain rule, this is where we do the differentiation. Implicitly differentiate both sides of the equation, and when we say the equation, we're talking about the equation we wrote in step 2, and we're going to implicitly differentiate both sides of that equation with respect to time. And when we do that, we will have an equation that's what we call a related rates equation. So it is in this step that we will get an equation showing the relationship between if we have two rates of change, or among if we have more than two rates of change, between or among rates of change that are given or to be determined. And after you do step 3, you do step 4. And the key word here is after. So you have to do step 3 before you do step 4. After completing step 3, substitute into the resulting equation, we're talking about the equation from step 3, all known values for the variables and their rates of change, then solve for the required rates, solve for the required rate of change. So we're going to see an example in which we implement these guidelines to solve a related rates problem. This is example 1 from the textbook, and here's the problem. And I just added the guidelines for solving related rates problems so you can see how we apply them for this particular example. So we need to begin by identifying all given quantities and quantities to be determined. Make a sketch and label the quantities. In this particular problem, a sketch is already provided, so we don't have to do that. But we do want to label any quantities that perhaps are not already labeled. So how do we identify all given quantities and quantities to be determined? You have to begin by reading the problem carefully. So we have here an airplane. It is flying 600 miles per hour on a horizontal path that will take it directly over an observer. The airplane is 7 miles high. So that's the altitude of the plane. And you can see that some of this information is already represented in the diagram. So the airplane is 7 miles high. So that's the altitude of the plane. It is consistently 7 miles above the ground. So that's already represented in our diagram. And here's the airplane. And make a note of the very first sentence. This airplane is flying 600 miles per hour on a horizontal path that will take it directly over an observer. So here's the observer, a human, a person, who's looking at the plane as it is flying towards him or her. And the very first sentence gives a rate. How do I know that 600 miles per hour is a rate? By the units. You can see the units for that particular quantity is miles per hour, and that's a rate of change. So that's how fast the plane is moving, and in which direction is the plane moving. It's moving horizontally, so the altitude of the plane doesn't change. It keeps moving 7 miles above the ground, but it's moving at a constant speed of 600 miles per hour. So that is a given quantity, and it is a given rate. So identify all given quantities. So we have identified one given quantity. It is a given rate. What do we want to find? Well, we have to keep reading the problem and make a sketch and label the quantities. Now, the other quantity that's given that is not a rate is the altitude of the plane. So now we keep reading. Part A. Write an equation for the rate of change of the line of sight distance z in miles between the observer and the airplane in terms of the horizontal placement x in miles from observer to the airplane. So let's go ahead and read that again more carefully so that we understand exactly what it is that we're being asked to do. Write an equation for the rate of change of the line of sight distance z. So here's the observer, here's the plane. And this is the observer looking at the plane. And this is called the line of sight from the observer to the plane. And there is a distance between the observer and the plane along this line of sight. And that distance is a variable. And it is a variable because that distance will change as the plane moves. So that's why that distance is a variable. And because that distance is changing, we want to know how fast is that distance changing, that distance between the observer and the plane, how fast is that distance z changing at a particular instant in time. So this is what we want to determine. We want to determine dz dt at a particular instant in time. And as it turns out for this particular problem, dz dt will be different at different times. And we'll see that. But that's the quantity that we want to determine. So let's read again. Write an equation for the rate of change of the line of sight distance z in miles between the observer and the plane in terms of x, which is also a variable. And what does x represent? It represents the distance from the observer to a point on the ground that is directly below the plane. So obviously this point is moving as the plane is flying. And x represents the distance from the observer to the point on the ground that is directly below the plane. And that point is moving, so the distance x is also a variable, just as the distance z is a variable. Now, what quantity do we know? Because in step 1, we want to identify not just quantities to be determined, but quantities that are given. We're given that the plane is moving at a rate of 600 miles per hour. And the plane is moving horizontally, which means this horizontal distance between the observer and a point on the ground directly below the plane will be changing at 600 miles per hour. So here's a quantity that's given. We're given that dx dt is equal to, I'm going to write negative 600 miles per hour. And you might think, why is Mr. U writing negative 600 miles per hour? The reason is because as the plane is moving, the way it is drawn in our diagram, the distance between the observer and the point on the ground directly below the plane will be decreasing. And because that distance will be decreasing, we express dx dt as a negative number. So this is a quantity that is given. And this is a quantity that we want to determine. Make a sketch and label the quantities. So we've done, the sketch was given, we've labeled the quantities, this is what we want to know, this is what we're given. And of course we know the altitude of the plane. It is a fixed constant, it is a constant 7 miles above the ground. And what you have here is a right triangle. So what is it that we want to do next? What we want to do is to write an equation for the rate of change of the line of sight distance z. In other words, this is our question, that's what we're after. But we won't get to that until we get to step 3. We've done step 1, but we can't get to what we want until we get to step 3. There is something that you have to do before that. And this is an equation that does not involve any rates of change. So step 2, write an equation involving just the variables whose rates of change either are given or to be determined. So the variables are x and z. And we're going to write an equation that does not involve dx dt or dz dt. By the way, this is dx dt. We're going to write an equation involving just x and z using what we have here in our diagram. So this is actually a pre-calculus part of the problem. You're just going to look at the diagram. You can see that you have a right triangle, and there is something called the Pythagorean theorem that relates x, 7, and z. So in step 2, you're going to write the equation a squared plus b squared is equal to c squared, or c squared is equal to a squared plus b squared, c representing the hypotenuse, and of course in our problem the hypotenuse is represented by the variable z. So we have z squared is equal to the sum of the squares of the two legs. So x squared plus 7 squared is 49. So that's what we have. And you can see that this is a pre-calculus equation. There are no rates of change here. That's what you have to do in step 2. Write an equation involving variables whose rates of change either are given or to be determined. So we're just writing an equation involving the variables x and z. The rate of change of x with respect to time is given, and the rate of change of z with respect to time is what we're after. But this is a pre-calculus equation. Now you do step 3. Once you have this equation, the next step is to, using the chain rule, differentiate both sides of the equation with respect to time. This is implicit differentiation, and we learned in the previous section how to do implicit differentiation. And then we'll go on to step 4 after completing step 3. So let's take a look at how we do step 3. So in step 3, we will differentiate both sides of the equation with respect to t, which is representing time. And this is called implicit differentiation. And the reason why we call this implicit differentiation is because we're making the assumption that x and z are differentiable functions of time, even though we don't know what they are. So when you see z squared, you see z squared as a composition of two functions, where the outside function is the squaring function and the inside function is z. And when you see x squared, you see that as a composition of two functions, where the outside function is the squaring function and the inside function is x. So now you're going to, on the right side, you have a sum, so you're going to write the derivative with respect to t of x squared plus the derivative with respect to t of 49. And of course, the derivative of a constant is 0, so this is just going to give you 0. For the other two terms, we're going to use the chain rule, and we're going to have the following. So we begin by taking the derivative of the outside function evaluated at the inside function of z, and multiply by the derivative with respect to t of the inside function. And we do the same thing for finding the derivative with respect to t of x squared. Take the derivative of the outside function, which is the squaring function evaluated at the inside function, and multiply by the derivative with respect to t of the inside function. And what is this? This is dz dt. And what is this? This is dx dt. So we will replace that with dz dt and dx dt. Now let's go back to our problem earlier. What are we looking for? We're looking for dz dt because the problem is asking us write an equation for the rate of change of the line of sight distance z between the observer and the airplane in terms of the horizontal displacement x in miles from the observer to the plane. So we will solve for dz dt here. So we get dz dt is equal to, you just have to divide both sides of this equation by 2z. So when we do that, we have 2x dx dt divided by 2z. So dz dt is equal to, 2 and 2 will cancel, so you just have x over z times dx dt. Furthermore, we know dx dt is negative 600 miles per hour. So we can replace dx dt because that's a constant negative 600 miles per hour. We can replace that with negative 600. So that will give us negative 600 times x over z. And the last thing that I can do is go back to my equation from step 2 of the guidelines, which is right here, and I can solve for z in terms of x simply by taking the square root of both sides of the equation. So z is equal to the square root of x squared plus 49. So I can replace z with the square root of x squared plus 49. So what I have now is what I want. An equation for the rate of change of the line of sight distance z in miles between the observer and the airplane in terms of x, representing the horizontal displacement from the observer to a point on the ground directly below the plane at a particular instant in time. So this is dz dt, the rate of change of this distance between the observer and the plane, the line of sight distance, given as a function of x, the distance between the observer and the point on the ground that is directly below the plane at a particular instant. So we have found what we're after. We have found an equation for the rate of change of the line of sight distance z in miles between the observer and the airplane in terms of the horizontal displacement x in miles from observer to the plane. So looking at what we've done so far, this is what we've done. In step 1, we identified the given quantities and the quantities to be determined. And a sketch was already provided. If it weren't provided, we would have had to do it ourselves. And we label the quantities as appropriate. But that was already done for us in this problem. In step 2, we wrote an equation involving the variables x and z. No calculus involved there, that's just pre-calculus. An equation involving the variables whose rates of change either are given or to be determined. In step 3, using the chain rule, implicitly differentiate both sides of the equation from step 2 with respect to time to get an equation that we're after, a related rates equation. And step 4 is what we want to do now. After completing step 3, substitute into the resulting equation all known values. We kind of did that because we substituted negative 600 miles per hour for dx dt at the end of step 3. And that's how we got the negative 600 here. After completing step 3, after you do the implicit differentiation, substitute into the resulting equation all known values for the variables and their rates of change. Then solve for the required rate of change. So with this now, we can do step 4. And in step 4, you might be asked, for example, how fast is the distance between the observer and the plane changing when the horizontal distance between the observer and the plane is, for example, 10 miles, when x is equal to 10. So what does that mean? That means you're going to take your related rates equation from step 3 and evaluate it when x is equal to 10, or whatever x may be, depending on what the problem is asking you to do. And we're going to look at that next. So that's step 4. So part B, plot dz dt. So in this particular problem, we can take this related rates equation and graph it on Desmos as a function of x. And remember what x is. It is the horizontal distance between the observer and a point directly below the plane. Plot dz dt as a function of x, sketch the result. So here's the graph of dz dt. That's the graph of dz dt, and of course this is the equation for dz dt. And it is given as a function of x, the distance between the observer and a point on the ground directly below the plane. Sketch the result. So what we can see is that when x is a positive value, in other words, when the plane is oriented to, in terms of this diagram, to the right of the observer, x is a positive value. And what's happening as the plane is flying in this direction? The distance between the observer and the plane is decreasing. The line of sight distance z between the observer and the plane is decreasing. So we would expect when x is positive that dz dt will be negative. So look over here, x values are positive 5 miles, 10 miles, 15 miles. And you can see that the dz dt values are negative because the distance z between the observer and the plane would be decreasing as the plane flies. And that's what we observe here. So when the plane is 30 miles away from the observer horizontally, the rate of change of the line of sight distance between the observer and the plane is about negative 584 miles per hour. That's how fast that distance z is decreasing at that particular instant in time when the plane is 30 miles away from the observer horizontally. And you can see that that's pretty close to 600 miles per hour because the further the plane is, the less there is a difference between z and x. So the rate of change for z when the plane is really far will be not that much different from the rate of change of x, the speed at which the plane is flying. However, as the plane gets closer and closer to the observer, what happens? You can see what's happening as the plane is flying, getting closer and closer to the observer. The rate of change, for example, when the plane is 5 miles from the observer horizontally, will be negative 349 miles per hour. So the distance between the observer and the plane when the plane is 5 miles from the observer horizontally is decreasing at a rate of 349 miles per hour. Look at part C. How fast is z changing when x is equal to 10 miles? So you just look at this table. When x is 10 miles, the distance between the plane and the observer is decreasing at a rate of about 492 miles per hour. So we're able to answer questions about dz dt at various points in time by using our related rates equation. So how fast is z changing when x is 10 miles? When x is negative 5 miles, that is 5 miles beyond the observer. So the plane will continue flying in the same direction. It'll fly beyond the observer, and at that point in time, x would become negative. So at x is equal to negative 5, you can see that the magnitudes are the same between x is equal to positive 5 and negative 5, but now dz dt is positive because the plane is flying away from the observer, and the distance, the line of sight distance between the observer and the plane would be increasing at a rate of 349 miles per hour when x is equal to negative 5, when the plane is 5 miles beyond the observer. So that's how we interpret the answer there. And then finally, interpret the graph in part B, which is what we're looking at here, when x is equal to 0 and when the absolute value of x is very large. So when x is equal to 0, what happens is the following. When x is equal to 0, the plane is directly overhead. And at that instant in time, the plane is still flying 600 miles per hour, but at the instant in time that the plane is directly overhead, the line of sight distance between the observer and the plane at that particular instant is not changing. That's why it's 0. Prior to that, the rates of change are negative because the plane is getting closer to the observer, and after that, the rates of change are positive because the plane is getting further away from the observer, but at that instant in time, it is 0. And then what about when the absolute value of x is very large? We actually talked about that before. When the plane is very far away, there is less of a difference between x and z. So the value for dz dt in absolute value will be close to about 600 miles per hour. So today we looked at these guidelines for solving related rates problems, and we were able to look at one particular example, and we saw how these guidelines are applied for that particular example.